beginning of the stream will just be like me figuring stuff out.
Yeah.
Where's the link?
Yeah, I can. Oh, okay, yeah.
Is it the stream URL? Doesn't make sense. Doesn't look like stream URL.
Maybe try sending that to me,
Yeah,
see if I can
yes.
open it.
Sending what? That
The
one?
stream URL, yeah.
I mean, it has nothing to do with like. There's no ID is the only thing.
Oh, I see, yeah. Go back to the stream. Click on the share button right here. Yeah.
Perfect. There we go. Can I send this to you?
Yeah.
How about I just push it in the general chat?
Yeah, just push it
In the general channel.
or the exact extension.
Is the general Discord channel like people could also view the stream that way?
Yeah, that's true.
How's the mic?
How's it? I think, yeah, we connected it to the screen.
Okay.
Yes.
And the live stream is okay?
I'm just double checking that right
Okay.
now.
Because there was like a setting in OBS that we needed to change.
What about it?
Is it displaying the full screen?
Yeah.
Okay.
Okay.
Oh, it's great, yeah.
It's great. Awesome.
Okay. Wait, where is the
I mean, people are still trickling in.
I'll call people, I'll tell people.
Yeah.
Post it on the Free Food Facebook page.
Oh my god.
Okay, so I'm about ready to start.
Okay, great. Okay, see you.
Okay, so I can start. We're all good? Should be fine. Okay, guys, so we can start now. We finally got the stream set up, so we can begin. So this workshop will be about convolutional neural networks. The week before reading week, there was a workshop about intro to neural networks. And towards the end, Jesse briefly introduced CNNs. So I won't assume that you've seen that, but I will go through that content more quickly than I would have otherwise. Yeah, so I guess we can begin. I posted on Discord, so the link to these slides will be up there, and then after these slides, I'll be doing a notebook. Yeah. It's invalid. Oh no. To this link. Oh, to join the Discord server. Okay, I'm not sure if I can fix that. All right, thank you.
Is it the one on the Facebook page in the description?
Okay. So hopefully this link does work. And after the slides, I'll be doing an example using convolutional neural networks, and that will be at this link here, and I'll show that at the end as well. Okay, basically it's just, before we begin, it's useful for you to have a basic understanding of what neural networks are, what supervised learning is. I don't need too much of in-depth, but just have a general understanding. Also, knowledge of PyTorch is useful, not required, and going to the workshop before reading week would also be very helpful, but again, not required. Alright, so what are we going to be doing in this workshop? Basically, there's this problem in computer vision called semantic segmentation. Semantic segmentation is sort of like classifying an image, except instead of just saying, is this an image of a cat, or a dog, or whatever, we actually classify every pixel in the image and say, does this pixel belong to a car, a road, a person, or say, I don't know, the sky, and that sort of thing. Which is a way more difficult task, as you can imagine. It's also very useful for autonomous vehicles. I think that's the classic really example of semantic segmentation. And that's where I got this image from. And so the idea is that we take an image, like the one on the left, and basically we just, like I said before, classify it and convert it to an image that looks like what we have on the right. Not exactly that image, but that's sort of the idea that we're going for. In this workshop, we're not going to be classifying something as complicated as a traffic image into cars and roads and bushes or anything like that. That's too much. I don't want to spend a long time explaining every concept. Instead, we're going to be doing something like, oh, I skipped a slide, this one, where we're classifying people's faces into what is a face, what is hair, and what is neither of those. So what is background, I'll call it. And we do this by using encoders and decoders. Encoders and decoders, just to give you a high level, because I'll go into way more depth later on, encoders take an image and they convert it into a high level description. So instead of saying just the low level pixel information of RGB values, they'll take that and say, here's a face, or here's a cat over here, and this is the shape of the face, and this is the shape of the hair, and that sort of thing. The decoder's job will be then to take that high level description and then convert it into pixel information again. So, just to show you on this example, we get this face, the encoder takes this image, converts it to a description of it. You can think of the description as maybe describing where the face is, where the hair is, what color the hair is, but in reality the description it comes up with won't really be understandable to us. But it sort of does something like that. The output, then the decoder takes that description and converts it into an image like this, where all the face and the hair pixels are. And so that's the task that we're trying to do, but we need to learn a lot more before we actually write the encoder and the decoder, because there's a lot of interesting concepts that we need to deal with. First off, I'll just quickly go over what a CNN is. A CNN is a convolutional neural network, which basically means that it's a neural network that uses convolution in its operations. What is convolution? Convolution is where you take two tensors or two matrices and you multiply sections of the first matrix by a second matrix, sum the results, and then store that in a new matrix. To explain what I mean by that, here's a nice little animation that we have. So what's happening here is we have three matrices involved. We have the light blue, which is sort of the input that we're processing. We have the dark blue matrix, which we call the filter. As we're processing the matrix, we take the dark blue matrix and basically scan through the blue matrix and multiply the matrices together and come up with the elements in the white. And so scanning through here, besides a very important characteristic of this operation that I'll touch on later, what it means is that we don't really care where, say when we're looking for a face or a cat or anything like that, we don't care where the image it is. We just want to be able to know there's a cat there, there's a face there, that sort of thing. But this is also really important because of, this sort of idea. So before I get into the actual math, let's actually talk about the purpose of these. Convolutional layers are inspired by our brain's optical nerve. Basically, the idea is they translate low-level features, such as pixel information, like RGB, into higher-level features, such as the presence of a line or a curve, and then take those and then convert them into the presence of an eye, a cat, a dog, an airplane, so on and so forth. And then we can do more with those from there. Okay, so now I just want to quickly run an example of convolution just to show you exactly how this works. Let's say we're looking for a line like this. It's a very simple task. We just have an image and we're looking, and we want to know where in the image is a diagonal line that goes from the top left to bottom right. So what we'll do is we'll take the matrix to the right here, which you can tell is sort of similar to the line here. And we're going to use that as the filter, the thing that passes over the input matrix that we're working with. All right, so now suppose we have these two images that we're processing. And let's say you take the filter that we saw in the last matrix and overlay it on the images that we see here. So in this particular case, you take this image represented as a matrix, and then we do element-wise multiplication with the filter here. So when we do that, what we get is that for this image, we get a value of 800 when we do element-wise multiplication, and then sum that up, we get 800. Doesn't really matter what that is. The important part is that it's bigger than the number 300. What it means is that the top image looks more like a diagonal line going from top left to bottom right than the bottom image, which we can all agree that that's true. if you want to quickly go through the math, the reason that is that the ones here don't line up very well with the hundreds on the previous. The ones here don't line up with the hundreds on the previous image, but the ones here do line up very well. And so you get a higher value, and so we can say this looks more like a diagonal line. So that's essentially what a convolutional layer does. It's looking for features that we're going to try to teach it what features to look for, but it's going to look for features like this. Okay, now just one more layer I want to cover, and then we can start talking about how we're going to structure the encoder, and then later on we'll get to decoder. It's called pooling. Pooling is important in convolutional layers because when you run a convolution on an image, you end up with, say, a new grid, and this new grid will sort of contain numbers like the 800 and the 300, and those will tell us, say, like, we might be able to say this 16 means that there is a diagonal line there, and this 1 over here means that there really isn't one. But we don't really care, we might not really care where exactly that diagonal line is, we just want to know a general sense. Or maybe we don't care at all where it is, we just want to know if it's there. In which case pooling is very useful, because it takes, say, an n by n square of this matrix and then converts it into one number. So in the case of average pooling, what we'll do is we'll take a square of 4 elements, we'll take the average of them, and that becomes the new 11.5 value you see up here, and then same thing for 1, 2, 5, 6, that becomes 3.5, so on and so forth. Then max pooling is simple, but similar in the sense that we'll take the maximum value. So this square right here becomes 16, this square right here becomes 14, and so on and so forth. If you want to think about the intuition behind this, the main thing is that we're looking for a certain feature, and when you run max pooling, then you can sort of tell that, oh, there is a diagonal line somewhere in the bottom right corner of this image. We don't care where in the bottom right corner, it just is in the bottom right corner. The other thing to note about pooling is that, I don't know, that's weird. Alright, this is the image I want to see. The other thing to note about pooling is that it makes an image smaller as we're going through the matrix. This is sort of intentional, also not really intentional, but it's just something to keep in mind because it'll be important for when we get to the decode. Alright, so now we can actually start discussing how we're going to encode the image. Before I do so, do you have any questions that I want to, because now we've really reached the end of the fundamentals, so before I start talking about the structure, are there any questions? Alright. Okay, so, as I talked about in the previous image that I just showed, the encoder is often going to reduce the width and the height of the image as it goes through the layers, and that's going to come up later. And then also the job of the encoder is to extract high-level features, so like the presence of in this case, the presence of like the shape of the face, or where it is in the image, or the shape of the hair, that sort of thing. And because of the pooling layers, the output of the encoder isn't going to be very location sensitive, in the sense that it's not going to really care where the hair came from. It's just going to say this is where the hair, maybe like this is sort of the shape of the hair as opposed to where the hair is. We'll deal with that later. So when we construct our encoder, we're going to construct it using this convolution block, which is basically a series of 2 convolutions and then some batch norms and rectified linear layer. I won't go into what the batch norm and rectified linear layer is, just because it's not really in the scope of this workshop. It was discussed in Intro to NN, if you remember it and if you were there. But basically, this is going to be the building block of our encoder. The image is going to be passing through this block over and over again. Right. So here's just another visualization. It goes in the convolutional layer. We run a convolution operation. Then we run a batch norm, rectified linear layer, and then we just do the same thing again. And now this is the actual encoder. Each of these double convolution blocks was the slide that we saw before. And then the max pooling layer is the thing that I was talking about, like the pooling where you take the maximum elements and simplify it that way. So we do max pooling a total of 4 times. So basically our image might start out at 128 by 128, but by the end of the encoder it's going to be something like 128 divided by 16, which is 8, I think. Doesn't really matter, but basically it's going to get much smaller, is the thing to know. Alright, so this is the end of the encoder, I'm pretty sure. Yes. And so that's basically the encoder is going to try to get a high-level description, is the main thing to take away. We'll have to come back to it, but for now we can move on to the decoder. The decoder is supposed to take the output of the encoder and convert it from a high-level description into an image again. So face, hair, that sort of thing. And so its structure will be surprisingly similar to the encoder, but there will be one key difference. Instead of taking pooling and all that sort of stuff, instead of taking pooling layers and making it smaller, we'll have to take that encoder's output and actually make it bigger. So we'll have to upsample it. And there's a lot of ways we can do that, and actually it's very important what way we choose. But there are 2 ways that I can think of the most important. And just to give a high-level overview, what we want to do is we want to take that output from the encoder and convert it from high-level descriptions, so like the shape of the face, the shape of the hair, and then actually convert it into an image, so pixel information. Okay, so there's 2 sort of conventional methods that are often used. There's something called transpose convolution and image interpolation. So transpose convolution is, you can think of it as sort of like the reverse of a convolution, and I'll go into more detail exactly what that is. Image interpolation is more understandable in the sense that if you ever resize an image on a computer, just make it larger, that's exactly what we're going to be doing here. We'll just take the output of the encoder and make it bigger. And then after that, we'll follow it up, usually in this field, we'll follow it up by another convolution, just to be able to interpret those values and not just say we're just resizing them normally. Yeah, in this case it won't actually affect us, but just for future reference, you'll have to follow it up with a convolution. Okay, so first I guess we can talk about transpose convolution. In this particular case, the green matrix on top is the input to the transpose convolution layer, the thing that we're processing, and then we're going to output the blue one. So what that means is that we take an element in the green one, and then we multiply it by our filter values, and then input all of the values into the blue matrix. And every time you see something overlap, basically we'll just have to add on to what's already in the blue matrix. So you can think of it like this. It's basically just the inverse of a convolution operation. Pretty much exactly the opposite. Okay, so I guess brief discussion of how convolution is actually computed. Just to maybe explain why it's called transpose, but also it's just fully useful. Suppose that we have this alpha matrix right here, and we have this filter A, B, C, D. And this is what we're going to run a convolution operation with. So what that happens is we'll have to run it through and just, as you can see on this sort of animation, we'll run the ABCD filter over the alpha matrix iteratively, and then we'll come up with the white output. That's sort of the theory behind it. But a way of actually computing it that's faster than just running iteratively is we actually form this matrix down here, and then we flatten the alpha matrix into this sort of vector right here. The reason for that is just going to mean that we have to do one matrix multiplication, and that's much faster and simpler. This operation right here is going to give us a 4x1 vector, which we then take and reshape into the actual output that we want. So both of these is going to do the exact same operation once we reshape everything that we need to do for this bottom calculation. And it does the exact same thing. It's just faster. Now, transpose convolution, so you can notice that this matrix over here translates from a 9 vector to a 4 vector. That's because what we're trying to do is we're trying to convert from a 3 by 3 alpha matrix into a 2 by 2 output matrix, if that makes sense. So then if you, when you come up with your filter matrix, then that would mean that you have a 3 squared columns and 2 squared rows. Now, if you want to do a transpose convolution, and this is the kind of the reason it is a transpose convolution, you can think of it as basically just taking the transpose of this matrix. If you flip this around, then all of a sudden it'll be converting from a 2 by 2 matrix into a 3 by 3 matrix, upsampling the image as we want it to. And so that's the reason it's called transpose. It doesn't really factor into the actual theory behind it, but sort of important to know, I guess. Okay, I'll stop here again just in case anyone has any questions. Just understanding this is sort of important before we continue on with the rest of the slides. Okay, good to know. All right, so we also have image interpolation. So as I described before, image interpolation is basically just you have an image on the computer. When you resize it, that's exactly what we're going to do here. There's a number of ways to do that. What we can do, I have listed 3 methods up here, there's even more. What we can do is something called nearest neighbor. And nearest neighbor looks something like this, where we basically just scale it up by a factor of up to 2 or whatever, and do something like this. I won't go into too much of the math behind each of these methods, but I just want to give you a visual sense of what they're doing. Because it does sort of factor in, like when you get the output of the algorithm, we're going to see some differences. All right, so then this is the nearest neighbor, and then more visualizations. So in nearest neighbor, you can see it's just sort of getting the closest one. But for bilinear, what we're doing is we're sort of just linearly interpolating along one dimension, and then linearly interpolating along the other dimension. And then finally, by cubic, we're actually using cubic equations instead of linear equations to get even more accurate sense, because now we're going to be looking at second and possibly third derivatives of the image. But this is all just to kind of do interpolation, basically what you'd see if you resize an image on your computer. And here's some more visualizations. Yeah, basically it's very smooth, and even bicubic you can tell is even smoother than bilinear. Okay, so that's the upsampling for image interpolation versus transpose convolutions. There are quite a few differences that honestly, there's so many differences I couldn't possibly go through all of them. But just some basic understanding of it. If we use a transpose convolution, what it means is that it'll the neural network as it's training will learn how to upsample the image. It won't just interpolate it like using this basic function. It'll actually learn and train its parameters to upsample the image in a certain way. This does require more processor power and memory, so maybe you're not able to run actual convolution, transpose convolution, so sometimes we have to downscale back to just upsampling. And this can also cause checkerboard artifacts, but I don't. Let's see. All right. Let's actually move on from those because I don't want to. It's a bit difficult to actually visualize what a checkerboard artifact is. But basically, when we look at image interpolation, what that means is that we'll have it'll be computing simple, defined functions and no real learnable parameters. It's just resizing it. Like I said before, you usually follow that up with a convolution. So in a sense that there are learnable parameters involved, but the actual image interpolation won't be learnable or trainable. Okay, so I will have both of these in the example that we're going to be doing. I'll be trying both upsample methods. I think it's difficult to exactly tell the difference when you train both of them and see what the output is. So in this particular application, it'll be difficult to see which one's better, but it's worth both. It's worth testing both anyway. All right, so just to remind you, we're going to be using the double convolution block again, 2 convolutions with some batch norm and rectified linear layers. Yeah, we've seen this. And then our decoder is going to look like this. It's going to have an upsample layer, and then a double convolution, and then basically if you notice, we're actually going to be upsampling like by a scale factor of 2. So in this case, we do 4 upsamples. So if you notice that, that means we're going to get back to the same size as our original image because the encoder made it 16th as small, like along both dimensions. This is going to make it 16 times as large. So we'll get back to normal. And then, just to quickly cover this single convolution, this is mainly just going to be, you'll be able to see it more in the example that we'll do, but this is mainly just going to be, we have all this information in this big image of all these channels, and we'll convert it back into something that actually classifies each pixel properly. But we'll see exactly what that means. Okay, we're not done. There's actually one very important thing that hasn't been covered yet, which is, well, very, very important. If you look at the image to the right, you'll see that it's pixel level accurate, and that's what we want. We want to say this pixel is faced, and then the pixel right next to it is not faced, or it is hair, or something like that. We can't do that if we just take the output of the encoder. Because like I said, the output of the encoder is talking about where the face is and what shape it is and all that stuff. We're not going to be able to extract pixel level information if we just have the output of the encoder. So we're going to actually have to have something, sort of a third component to a network besides just the encoder and the decoder to get this sort of pixel level and precision. This is going to be called a skip connection. The idea is that we have the encoder running its operations on the network, and then we have the decoder running its operations. But in between, instead of just passing it from the encoder and the decoder, we'll actually take the outputs of other layers of, layers in the encoder and pass it directly to other layers in the decoder. So we'll skip basically large portions of the network, and this is why it's called a UNet. I'm not sure if I've mentioned that word before, but UNet is basically something with skip connections and an encoder and decoder. It's a U. So that's why it's called that. Skip connections are any form that take the output of a layer and then pass it to the next one. And there are a number of ways to do that. I'll talk about 2. I think, so one, we'll use this way. So basically we'll take the output from a previous layer, which I have a demonstration. Yeah, so we'll take the output, say, from this double convolution, and we will take the concatenation, and we'll concatenate it to, I'll use my mouse to this. We'll take the output for this double convolution, and take the output of this double convolution, and we will concatenate them together. And then we're going to give it to the upsample layer. Does that make sense? Is everyone sort of visualizing that correctly? Like we have sort of 2 images, one image from the first layer of the double convolution of the encoder, and then we have an image from the second last layer of the decoder, and then we concatenate them together, and then we keep processing them. Now the reason for doing this, and then we also do this again for this layer and that layer. The reason for doing this threefold, or actually possibly even more than that, it fixes a few things. So the vanishing gradient problem, for those of you who don't know, is just the idea of if you have a really deep network with lots and lots of layers, and you try to train it, as the training algorithm propagates backwards to the network, the gradients that it's going to be, the amount that it's going to be changing the parameters is going to be decreasing, decreasing, decreasing. But now we're actually taking the output from a layer all the way at the back, all the way at the front of the network, and we're taking that output and plugging it into almost the last layer of the network, which means that those gradients that train the first layer are going to be much larger and much more important in the output. So this sort of helps solve that. The other one is the residual function, which is a little bad name. What I mean by residual function is the people who first designed the skip connection designed something called ResNet, and their idea behind that was, suppose that this network, jump to this slide, suppose that these layers right here, from max pool up until, say, upsample or double convolution, that they're for some reason just not doing what we want them to, or they're just doing a really bad job. What that means is that at the very least, this upsample layer, or this double convolution, can learn to ignore all of the output coming from here. So even if this is doing a really terrible job of computing whatever it is we want it to compute, at the very least we can learn to ignore it, and so then we can say, at least this network isn't going to be doing worse. It's going to be doing exactly as, it's not going to be doing worse just due to these extra layers. So that's one extra thing. And the third benefit is what I was talking about before, which is basically the pixel level sort of information. If you look at over here, when we take the output of this double convolution, then that double convolution, the output of that still contains a lot of information about the pixels and what each pixel corresponds to. Actually, since we haven't run a pooling layer, it actually contains every bit of information you can think of. And then we take that and we plug it into the very last layer, and so that last layer now has all of that pixel information it needs to process and that sort of thing. And then we have other skip connections just to allow that sort of similar functionality throughout the network. Okay, I think we can move on to the example. Do you want me food break now? We have a lot of pizza, which is sort of lucky for you guys that everyone else is at their midterms and that sort of thing. So, food break now or food break after? Now? Now, all right, now. Oh, it's backwards?
Yeah, I understand. more precise and more
So what batch almost done is it's basically making sure that the output is at the very least going to maintain a similar distribution. Even if you change what around the other layers. So it's basically helping it sort of stay the same. Yeah, stabilizing things even as you train it, so then other layers can still get the same or similar. There's definitely more mathematical way to do it, and that's what everything in neural networks is intuitive explanation, but there's a more mathematical explanation. And that takes a lot. Even I don't believe
Yeah.
So like, you know, when you take the math and pixels from 0 to 0 to 1, to make them small because are better and then that was does batch constantly the same thing?
so batch does so batch does is normalize it to the distribution, but not necessarily like how you look from one distribution. It actually has to turn around with learn. So it's not necessarily it's just making like to that so it does not and it might also
Okay. So we can now start on an example, unless you guys want to finish your pizza. I don't know. Yeah, at this point, if you have your laptop and you're following along, you just have to press like play on various code blocks. Yeah, all right. So if you open up the link at the last slide and also the second last slide, I think this presentation at CNN Notebook F19, it should take you to here. Since you're not signed in as me, I think there'll be kind of like a run in playground button on your top left. Click on that, and you should be able to run everything and just fine. If you are running everything, when you hit connect, make sure to run it with the GPU, basically, because otherwise it's going to take forever to do everything. So we'll say change runtime. Oh, I'm already on GPU, but that's good. Okay. All right. So right now, basically we've designed the encoder, we've designed the decoder, and all the skip connections that come between them. So now I'll be using the PyTorch library, basically to construct exactly what I just said. There is a lot of details though about. We just talked about designing the model. There's a lot of details about preparing the data that's going to go into this model. So first, I've done some of the work already that's not in this notebook. Basically, I have two zipped up files where this file right here, this link, contains all of the faces that we're going to be processing, the actual faces. And this file right here is going to contain all the segmentation masks. So by segmentation mask, I just mean the image on the right. And so just real quick note, hair is encoded as 255, like in terms of RGB values. Hair is encoded as 255, face is encoded as 127, and background is encoded as 0. This will be just sort of important for details. Anyway, so these folders are present at this link. I download them into the Google Colab server, and then I unzip the folder into, actual folders. I unzip the file into actual folders. So just a quick cover of what we're going to be using all these libraries for. Torch, we'll be using them for deep learning. NumPy and CV2. CV2 is OpenCV. We're just going to be using that for loading in the images and preparing them. And then OS glob is just to process some file paths that we're going to need, again, to load in the images. And then TensorBoard is going to be important. It's basically something we can use to visualize how our algorithm is training. Slight warning, I'm not going to train the algorithm here because it takes a long, long time. Even 20 iterations of the 20 epochs of training it takes, an hour or so, and I don't really want to just stare at the screen for an hour. And finally, we have matplotlib, which is just we're going to use to show the images and what they look like. Okay, so we can run that. Okay, so that's running up now. Now we're actually going to load the images in. So we'll ignore these functions for now, and I want to start at here. It's quite simple what these do. Basically, I'll just be looking up, I'll have a list of all the faces in the face image, and then I'll have a list of all the segmentation masks in the segmentation folder. And then what we want to do is we want to pair them up, because we know the face, the file name of the face is going to be the same thing as the file name of the segmentation mask. So that's what this is going to do. This is going to pair them all up. It's a fairly simple, process. Now, one thing to note is that when OpenCV reads an image, which it's going to be doing right now with this line right here, is it takes an RGB image, but it's not going to store it as an RGB image. It's going to store it as the BGR image, which basically just means that instead of it's going to swap around the R and the B, which isn't important for training because the neural network doesn't really care what is blue and what is red, but we care because we're going to have to see it at the end because we're going to want to see how our images are working. So it's just easier for everyone if we swap it at the beginning, which is what this sort of line does. Then, just to make things nice and simple, what these lines do is we're going to crop the image into a square. So I'm not sure if the image is a fixed size or whatever, but I just said if it's wider than it is long, then I want to crop it so that it is wide. It's exactly as wide as it is long, and likewise if it's vice versa. Basically, we just want to make it into a square. Once it's a square, then we want to resize the image into 128 by 128. To be perfectly honest, 128 was not really, I didn't really choose it for a particular reason, other than it's a power of 2. It just seemed like a good image size that we didn't lose too much resolution, but it's also small enough that it didn't use up too much memory when we were training. This could easily be, 64 by 64, or 256 by 256. And then finally, we have to do one more important thing to note. When we're converting into a torch tensor, so right now it's a NumPy matrix. If any of you use Python, NumPy is just a number processing library. Right now it's just a NumPy matrix. We're converting into a torch tensor, but we'll also, how to best explain this? An image, when it's read in, a NumPy matrix is organized by height, then width, then channel. That's sort of the order of the dimensions that's stored in. But a lot of the operations in PyTorch expect the channel dimension to be first. So that's what this is going to do. This permute function right here is it's just going to move the channel to the front of the line. So now everything for the first index we pass into this tensor is going to be the channel instead of the height, that sort of thing. So now we're going to do that's processing a face. We do something slightly different, just ever so slightly different when we're processing a label or a segmentation mask. When we read an image from the segmentation mask, here we have the OpenCV BGR image. But then, if you go back to the slides, you can tell it's grayscale, which means that every channel is the same. Like they all they all sort of have the same value. So, and this is important for us. So what we do is we strip it from, we strip off the first layer, or the first channel, so the 0th channel right here, and then we divide it by 255, because we know that, like suppose hair is equal to 255, face is equal to 127, and then background is equal to 0. We divide it by 255, which should allow it to be, which should scale it from 0 to 1, and then we multiply it by 2, which means that now the new values that we're going to have are 0, that represents background, 1, that represents the face, and then 2, which represents the hair. Basically, this is just going to represent unique IDs that we have to classify each of these, classes. Because the classes we have are background, hair, and face. Okay, and then we do a similar thing. We crop the image, resize it to 128 by 128, and then note that we don't really care about the size, the channel, or anything like that, just because it's not the same shape of as the face image. All right, we now have all of the images loaded as torch tensors, and so we're almost ready to come to process them, except we have validation, validation proportion of 0.91. So when we have this validation proportion, that basically I'm just saying that I want the validation data set to be about 9% of what we have, and then the rest of it to be 91%, which we can see exactly here. Did I run this? Okay, so now we run that. Here, I already went through all of this sort of on the slides. I'll go through it again. We have the double convolution and all the up convolutions and that sort of thing. There are some details to cover for the up convolution though. And then we have a main UNet thing. Okay, so real quick, double convolution has, as I described it, it has a convolution, then a batch norm, and then a rectified linear layer, and then and then that's sort of the end of it. It's using a 3x3 kernel filter. So if you go back to this sort of idea, if you see how that this filter is 3x3, that's sort of what it's doing. And then it's also doing a padding of 1, which basically means that it should pad this sort of blue matrix by a value of 1 on outside. Sorry, it should have an element, a ring of zeros around this blue matrix, which basically just helps us allow to, when we run this convolution, the image is basically going to be the same size as when it came in. That's all it's necessary for. Okay, so we have the double convolution. Now we're going to use it for various things, such as, let's go to the down convolution first, where basically a down convolution is just, you run a pooling operation on the image, and then you run a double convolution, as described in the slides. And so if you can see here, what we do is we say, first I want a double convolution. So a double convolution that takes the number of channels in the image, which are 3, and then we run them and convert them into 64 channels. So the output of this is going to be, oops. Yeah. So instead of 3 channels and 128 by 128 pixels, we now have 64 channels and 128 by 128 pixels. And then we basically keep doing this, and as you notice, we're doubling the number of channels, but we're also having the image. So we're basically we're redistributing the data. And so at the end of it, I think we have something along the lines of 512 channels with, I'm pretty sure, 8 by 8 pixels. It's not too important, but it's around there. Okay, So now we have 8 by 8 pixels. So the down convolution is easy sort of to understand, but now we have the up convolution. So the first thing to note here is when we construct this module, is we're saying if you want to use image interpolation, which is to say, bilinear or nearest neighbor and that sort of stuff, then we will say the up layer is this, which is PyTorch's sort of functionality to upsample a layer. And then if we want to use, that's not supposed to be there. If we want to use transpose convolution, then we'll do exactly this, which is to say it will run a transpose convolution on the input. Okay, now exactly how we do that is a bit more detailed than what I said in the slides. Remember, the idea here is that we want to take the input from, one sec, let's see if we can grab that thing here. We want to take the input from a previous layer and the input from, say, the immediately previous layer, concatenate them together, and then plug them in, actually into the double convolution. This structure is a little long. So first of all, we upsample the image from the immediately previous layer, and so we scale it by a factor of 2, using transpose convolution or whatever. Then, just because we can't really be sure that the sizes of the images are exactly the same, and we do want to concatenate them, so we need to make sure the images are exactly the same size, at which point we'll calculate the difference between the two images, and then we're going to pad the upsampled, or the input one, basically, to make it exactly the same size as the output from, say, the previous layer, or the far back previous layer. Now, we pad it, we have that. This line right here concatenates them along the channel axis, which is to say, it's not along the height or the width axis. We want to concatenate them along the channel axis. At which point, then we run the double convolution block that we talked about in the slides. Okay, so that's the up convolution. Any questions so far? Okay. Should I slow down when I'm discussing this, or this is a fine speed? Okay. Okay, so now we can actually construct a UNet, which, if you remember, is basically something like this, or any network with skip connections and that sort of thing. And then one important note is that when I tell the up convolution how many channels I'm giving it, you can note that it's not just 512 and then 512 plugs into here. That's how it was with down convolutions. But in this case, we're actually taking 512 channels from this layer, and then we're going to plug it into this up convolution, but it's going to be accompanied by, the output from this layer. So it'll be 512 plus 512, which is 1024. Then this up convolution is going to convert that into 256 channels or layers, and then that 256 again will be appended to the output from this layer, which will be 512, so on and so forth, until we get to 64 channels at the end. So now we have 64 channels. If you recall from one of the previous slides, the decoder that I just described had a single convolution. We want our network to output an image that looks like this. But we can't just output, it can't be just an image that has 0, 1, or 2, where we want it to be 0, 1, or 2, because when we train a loss function on that, then what we're telling it is that when it classifies a pixel to be a face, it's halfway to classifying it to be a hair pixel, which is wrong, which is not really the relationship that we want to construct. So instead of constructing it to be just output of a picture like this, where 0 means background, 1 means face, and 2 means hair, we'll actually be outputting 3 channels to represent our 3 classes of background, hair, and face. And so that's what this is going to do. So when we interpret these channels later on, the loss function or whatever can sort of interpret it how it wants. But when we interpret this later on, we'll say we have 3 channels in the output, right? If we look at a certain pixel, that means we have 3 values for that pixel. Whatever channel has the highest value, that means that's what we're going to take that pixel to mean. So if it has, if a pixel has, say, 0.5, 0.2, and the channels are 0, 1, and 2, if the pixel value at a certain location is this array, we're going to say, okay, so then our network believes this pixel is background pixel, because that is the highest value. That's how we're going to interpret it later on. Okay, so that's the output of the UNet. That's the entire structure of the network. We've prepared the data, probably accurately. I ran this numerous times, so I'm almost certain it's accurate. And now we should be ready to actually run the optimization thing. I'll explain this later. You'll see exactly what I mean by it. And when it comes to various numbers of this, so like I have batch size 32, epoch 20, and I think, let's see, a learning rate of 0.002. What I want to do is not really make a product, like a productized model here. I just want to show you guys how these techniques work and why some techniques work better. So these aren't tuned at all, really. I just took the values that I'm used to using when I use convolution and various techniques like this, at which point I'm using an atom optimizer, these learning rates and these parameters, and then I'm using a cross entropy loss function, which I won't go into exactly. Okay, so again, so we have a batch size of 32, which means we take 32 images at a time, and then we run it through the network and then train that. We can probably have higher, because at the moment this network doesn't use too much RAM or too much memory. I don't think so. And then beyond that, we do this for 20 epochs. Finally, we have a PyTorch data loader, which you don't need to know. If you don't know PyTorch, basically it's just going to give us the images in batches of 32, because we told it to give us batches of 32. And if you recall, all the way up in this block right here, we've set train data and test data. So that's where it's actually fetching the images. Okay. And then finally, we tell it I want to use a GPU. I want to use the UNet with various parameters. So we say the input image is going to have 3 channels, RGB. And I want to have the output image to have 3 classes representing background, face, and hair. And then for now, actually, let's turn that into, let's just use transpose convolutions. And then we tell it, put that on the device, put that on the GPU, initialize the loss function, the optimizer, and I will get to the TensorBoard sort of the logging information. It's good to visualize it. And so the rest of this is sort of a fairly basic, oh look at here, great. Fairly basic, what am I saying, training sort of system. I'm using, I'm fetching the image, the face image, the label, which is the segmentation mask, and remember that this value is 0, 1, or 2. Sorry, it's an image where each pixel is 0, 1, or 2. And then I'm telling it zero out all the gradients that we've currently learned for all these images, and take the face image and run it through the UNet. Now, put that at the back. Okay, so now if you recall, what I was talking about before, where the torch tensor expects the channel to be sort of at the front of the image, so it goes channel, then height, then width. We want to reshape that differently because the loss function is going to expect a 2-dimensional matrix where, and so we basically need to flatten it into a 2-dimensional matrix, which means that we need to put the channel axis at the back of the image and then flatten it so it's into 2 dimensions. Okay. So now we have it flattened into 2 dimensions, and again we have a label which is an image of 0, 1, or 2, and we flatten that label and plug it into the loss function. If you're curious about why I have just torch.flatten here, it's just details with the loss function and how it's implemented in PyTorch. It's very well explained in the documentation. we have the loss output, we run back propagation, and we make a step with the optimizer. Okay, so how about I actually run this, and we can see exactly why I have all these lines called TensorBoard or whatever throughout the code. They are very useful, I can promise you that. Without TensorBoard, what we'd be looking at is just numbers printing on the screen. And it's interesting if you know what they mean, but TensorBoard is still nicer to have, if it'll open. Let's see, okay, great, so that output is there still. All right. Okay, so while TensorBoard is opening, hopefully soon, I can explain the rest of what I'm just doing here. Great. So basically all of these lines here is just logging all of the loss functions. The cross-entropy loss function is measuring the distance between our prediction and the true answer. So we want that value to go down. And then every epoch, we can change this to speed things up. We take our model, we run the validation data set that I split up. Remember, it was like 9% of our actual total data sets. We take that data and we run it through the network again, and we calculate the average loss function that it creates. So here we can tell that it's actually, the loss function is decreasing quite considerably. It started around there we go. It started about 1.14, and now it's at about 0.5, which, to be honest, you can't really understand in any visual or intuitive sense, but what it means is that our network is improving, theoretically. And then as this keeps processing, we can tell, or hopefully we'll be able to see a certain validation loss. And so we can see not only how a network is performing on the data that it was trained on, which is not that useful because it's already seen those images, but also how it's actually performing on images that it hasn't seen so far. So while it's doing that, I can show some example outputs. I don't want to run this entire thing, so hopefully we still have that output. Okay. So after 20 epochs, we can see this sort of output, basically. You can tell that, so just to explain the classes, this is the phase we're processing. This is the ground truth, which I'm looking at this one. I don't think that makes sense, because he doesn't have hair. But whatever. Anyway, so that is the ground truth. And so honestly, you can't really blame a network for being very confused. This person has hair, and the network sort of understands it. But here you can see that it's getting a bit, it scored quite well here. It mistook something over here, kind of got this hair quite well, and that one. And you can keep looking through the entire validation data set and seeing how it performs. Because the main thing that I want to get across here is that I've explained how to use transpose convolutions. If I can scroll up to the network. Like this is right here, what we have is a fairly simple UNet. It's using batch swarms and rectified linear layers and convolutional layers, and those are all key things to every network, but there's a lot of things that it's not using that are actually very important. And so what we can do is we can just increase the number of layers. That's very nice and a very simple way of doing things. But there's also a lot of tools. If you go back to the very beginning of the slide, I have an image like this, which basically is talking about autonomous vehicles using these UNets and that sort of thing to classify an image like this. You wouldn't be able to use the UNet we're using right now to accurately do this. It could sort of do a good job, but you need something better usually. And the interesting thing, at least I think this is an interesting part, is that when you actually use these UNets, when I talked about having encoders and decoders as sort of a two-part to the network, you can actually use them as two parts. So then you can say, you can take this particular encoder and this particular decoder and then sort of couple them together and see how that performs. So I know on Autonomous, if you guys know about it or on that or whatever, the perception team is currently researching into various algorithms that they can do to perform exactly this type of process. And so they're looking at various encoders and see how they pair up with various decoders and that sort of thing. Yeah. So I guess we can jump back over to where this looks like, where the training is. And we can see, oh, I think it might be doing something else I wanted to talk about. All right, so here we can see it's dropped down to about 0.2, and then for some reason it's now back up to 0.39. And this validation looks very odd. But basically it is improving. I think I did want to wait until the training approaches a certain key. There we go. Okay, so see this peak right here? It's jumped all the way to 0.662, which is very much not what we want. I didn't want to fix this because I actually want to point out this. When you have a certain, how to best explain this? When you have like this really deep network here, what you can tend to have sometimes is sometimes the gradients, when it's sort of figuring out how to change every parameter, they can explode, which is to say that they can get very large. Once that happens, if the network makes a step in any direction, it's going to change the output of the network drastically, which might be a good thing, but in our particular case, obviously it's not, because it got way worse. Thankfully, it fixed itself pretty quickly, but I'm pretty sure another spike happens as you train this. And so again, we don't want that to happen. So that's another improvement. Is basically all I wanted to point out. You can make sure that the gradients never go past a certain limit, and that's also something important. Do we have any questions? Now, I feel like I just threw a bunch of information at you guys. But there is a bunch of information to be thrown, so. Okay, oh yeah, do you have a question?
Well, yeah, just if we go back to the architecture of the network.
On the code or on the slides?
I guess just the UNet model.
Okay.
Yeah, so I was wondering, can you go over the part where the convolution, once it's taking in 1,024 channels, that you stack the output of the downsampling, and I guess you stack the other?
Yeah, okay, so actually this is something, so if we have, look at over here, right? So we have, in a sense, this section right here is the down convolution, is the encoder. And so we're taking the output of the last layer and the second last layer, and then we're putting it into, this is actually incorrect. One sec. That's actually the real thing we're doing here. We're taking that layer and passing it into this double convolution, which is to say, so we're taking the second output of the second last layer and the last layer and passing it into the first up convolution, which is exactly what we're doing here. The last layer has 512 channels. The second last layer has 512 channels. So we plug that in and concatenate them, which has 1,024. And we do that for every other network, which is why this is double everything else too. Any other questions? You can also come down and talk to me more about the stuff if you want afterwards. Okay, that is the end of this workshop. Thank you for coming, even though you probably all have midterms in about this time. Oh, also, you're welcome to get more pizza.
Telling us the state of the art of machine learning. We so saying it's not actually original. I see your path.
Really? Because I can't. What's the end parameter of the rabbit? And now, like, I don't know, numbers being a rabbit.